In this video, we're going to do some analysis, that is running time analysis of stacks and queues. If you have not watched the videos on stacks and queues, this probably will be a good time to watch all the videos related to stacks and queue and make sure that you watch all the different implementations for stacks and queues. As discussed in those lectures and videos, the analysis of the running times for stacks and queues will depend on the implementation. And typically, stacks and queues are implemented using either an array or a linked list. That's what we call array-based or reference-based. Let's just start with a stack. So if we're going to use an array-based stack, essentially we're using an array, so we have indexes, but we have to keep in mind an array has a limited size. It's not a dynamic data structure. So we may run into a problem. We'll talk about that in a couple of seconds. So as you can see, the three basic operations on the stack: push, which is to add, pop, which is to delete, and pick, which is to display the top of the stack, they all happen to be in constant time. Remember that O1 means that this is independent of the size of our data. So we could have a stack which is very small or a stack which is very, very large. And the performance of the push, pop, and pick will be completely independent of the size of the data. And the amount of time will be constant. So whatever amount of time it takes, it is totally independent of the size. That's actually very, very good news. But when we use an array implementation, we have a limited size. We have a limited numbers of elements because we're using an array. So what happens when the stack is full? What happens when the array reaches maximum capacity? So here you need to understand the following. We have a couple of options. One option is for our implementation to simply say the stack is full and that's it. So we're not allowing to push to add any new values onto the stack. If you look at the implementation that I provided using an array, that is the case. You will see that there are some error messages indicating that the stack is full and there's nothing to be done. Now, a second option could be something that sometimes is done, which is to increase the size of the stack. In other words, we change the size of the array that we initially started with, and then let's say we double the size, creating a new array, and then we have to copy the old values into the new array, and so we end up with an array that is larger, an array that contains the old values. Now, there is a price to pay for doing this. The process of copying from the old array into a bigger array is definitely going to be dependent on how many elements we need to copy. So if we decide to double or increase the size of the original array so that we can push more elements into the stack, then our operation to insert, which is push, will not be any longer constant time. It will be ON because, again, copying the old elements into the new array will be directly proportional to the numbers of elements we need to copy, therefore ON. Again, that is if we decide to change the size of the stack. If we simply notify the user indicating that the stack is full, then there is nothing else we have to do. A different issue comes with the implementation of the stack using a linked list, which is the reference-based implementation. And in that case, this is a dynamic data structure, okay? Because we're using a linked list. And as we know, linked lists can grow and can shrink dynamically. And that means that the same three operations that we discussed, the push, the pop, and the pick, all of them are independent of the size of the data, and their respective running times are constants. We don't have an issue with the size because we're dealing with a linked list. Now let's talk about the queues. And again, we're going to discuss the same two implementations. So in an implementation for arrays-based queue, the operations for enqueue, which is add, dequeue, which is delete, and pick, which is simply display the element at the front of the line or the queue, they are all O1, which means, number one, they're constant time. And what that means is that the performance or the running time of each of these three operations is independent of the size of the data. So the queue could be a very small line, could be a very large line. the expected running time of these three operations is not affected by the size of the data. But let's again go back to the same issue that we have with the stack. What happens if we implement a queue using an array? Well, that means that the array is going to have a finite size. It's not a dynamic data structure. At one point, we could be using all the elements that we have on the array. In other words, the queue is going to be full. So what options do we have? Same two options. Option number one is to simply display a message and let the user know that the queue is full and that no other values can be in queue. If you look at the implementation of a queue using an array that I provided with, this is the case. I'm printing an error message saying the queue is full and I'm not allowing the user to enqueue any other elements in the data structure. The second option is the same as the one we discussed before. We change the size of the array. And what that means, perhaps, is we're going to double the size of the array, which will be effectively double the size of the queue. So we need to create an array which is twice the size of the one that we have. And the second part is going to be copy the values from the old array into the new array. So the operation of copying the values from one array to the other is the one that is going to slow the process of enqueuing. So it's not so much adding a new value at the end of the queue, but the fact that because the queue is full, we are going to create a new array and we need to copy the values from the old array into the new one. That operation is directly proportional to the size of the data. Its running time is O(n). Okay, so now we're introducing this O(n). So we will say that the enqueue operation, if we are going to resize the array, is not longer O(1), is O(n). The implementation of the queue using a reference is using a linked list, right? As you remember prior the previous discussions. And again, the enqueue, the queue, and pick at all times is going to be O(1). Remember that in the linked list implementation for the queue, we have a reference telling us where the first node is, the front of the queue. We have a separate reference telling us where the end of the queue is, the last element. Therefore, if we need to enqueue, and that means add a value at the end of the list, we know where the end of the list is located. If we need to dequeue, which means remove the value at the front of the list, we know where the front of the list is also located. So those are completely O of 1. And obviously displaying the value at the top, at the front of the queue or at the beginning of our linked list is also O(1). So very good news that all three operations, enqueue, dequeue, and pick in the reference-based queue, they're all constant time and they're independent of the size of the data. Finally, let's talk about priority queues. And again, two ways of implementing the priority queue. One is using an array. And again, the discussion is exactly identical to the regular queue. The only thing that changes is the enqueue. Remember, enqueue in a priority queue means that we're going to use a priority, a given value, to insert the objects into the queue. So we no longer follow the rule that says add the new value at the end, like we normally would do in a regular queue. Because of that, once we find a place of insertion, we're going to have to copy down in the array. We're going to have to shift elements to the right of the array so that we can insert the new value, the new object, in the indicated location. And that location, again, is given by the priority. So the expected running time is going to be O(n), because on average, we have to probably move half of the elements, and that approximates to n. Now the dequeue, which is the process of removal, continue to be the same. We remove the value which is at the front of the queue. And the pick is not affected. So the only one that is affected is the enqueue. Again, remember that we have a special case of when the queue is full and we have a decision to make whether or not we're going to double the size of the array or simply tell the user that the queue is full and no other elements can be enqueued. Now, if we use a reference-based implementation, the analysis for the enqueue continues to be the same, but for different reasons. So why is enqueue proportional to the size of the data? Well, It is because we have a linked list, and remember, linked lists have no indexes, right? So if we are given a priority, we're going to use that priority to find the place of insertion. Well, there is no other way of finding the place of insertion in a linked list but to traverse the list from the very beginning. So if we're given a certain location, or we're being told that the priority is to keep the values, let's say, in alphabetical order, then we will have to traverse the linked list. We will have to traverse the queue starting from the beginning, traverse the linked list one node at a time, one by one after the other, until we find the right place of insertion. Again, on average, it means that we're going to have to traverse half of the list on average. And that is why we say that the expected running time, which is an average running time, is ON. So happens to be the same as the enqueue for an array-based implementation, but the reason is for different reasons. So dequeue and pick methods are constant, so they remain the same. We can see using priority queues, even with an array-based implementation or a reference-based implementation, we are making things a little bit worse because the expected running time goes from O1, which is constant and independent of the size of the data, to be proportional, directly proportional to the size of the data.